Okay, nothing like a bit of Brazilian jazz to get us warmed up for solving stoichiometry problems. I'm just going to turn this down a little bit. Alright, that's better. So now hopefully you can hear me okay. So this is going to be another stoichiometry problem, and I'm going to show you how to, a quick video to show you how to deal with some gas stoichiometry. Remember, gas stoichiometry, two things you have to consider with gas stoichiometry, and that is Gay-Lussac's law of combining volumes. I'm going to show an example of that, and the use of the ideal gas law, or ideal gas equation, PV equals nRT, which you might remember. So let's get stuck into it right away. Alright, so here's a question. Combustion of propane proceeds as follows. There's propane C3H8 plus oxygen yields carbon dioxide and water. You should know what type of combustion that is given that chemical equation. That type of combustion is... Good. Alright, so here's the question. If in the lab 5.05 liters of propane reacts with 45 liters of oxygen, what volume of carbon dioxide is produced? So, two things you should recognize from this question. The first thing is that it's a limiting reagent problem because we are given two volumes. We're given a volume of propane and we're given a volume of oxygen. So that means we have to find the limiting reagent. The second thing you need to recognize is there's no mention of temperature and pressure in this question. So we can only assume that the temperature and the pressure is constant throughout this reaction. Therefore, all constituents of the equation have the same temperature and pressure. So that means we can use Gay-Lussac's law of combining volumes, which says that if the temperature and pressure of reacting gases are the same and the temperature of the gases produced is the same, then volumes of reacting gases are always in whole number ratios, or react as whole number ratios. And that's the same as looking at them as equation factors. So let's answer this question. Well, the first thing is limiting reagent. Well, we have 5.05 liters of propane and we have 45.0 liters of oxygen. Which one runs out first? Well, the really quick way to do it is divide by each coefficient. Because they are at the same temperature and pressure, we don't need to find number of moles. We can just divide by their coefficients. And so what we get is 5.05 liters propane and 9 liters oxygen. Which number is smaller? Propane. Propane is limiting. And remember, whenever you answer a limiting reagent question, I do want you to state what's limiting. So you just got to say that. Therefore, propane is the limiting reagent. Okay, so now we've done that, it's really simple because we're just going to use the coefficients in the equation and we're going to solve it using equation factors. And so that is simply volume of CO2, that's what we're looking for, equals volume of our limiting reagent, that's volume of propane C3H8 times an equation factor. And if we go to our equation, the relationship between propane and CO2 is a 3-to-1 relationship. So 5.05 liters propane times 3 moles CO2 divided by 1 mole propane. Propane divides out and moles divide out, and so we're left with a unit liter and CO2, and we get an answer of 15.15, which we round to 15.2 to give correct number sig figs. Constant constant pressure and temperature, use Gay-Lussac's law, makes gas problems really simple. Okay, so if you look at the second one, part D, we've dealt with part A already, so volume of carbon dioxide produced. We're going to ask the next question, what volume of water vapor is produced? And so a couple of things. I have changed the question a little bit. You will notice we can still use Gay-Lussac's law of combining volumes because I've not added any information about temperature and pressure to anything. I have removed any information about oxygen and said it's excess oxygen, so it's no longer limiting. So yay, that makes life a little easier. I wanted to give you this question because there's two ways to answer this. So first way is using the molar amount of, the volume of propane. So we simply use volume of propane given 5.05 liters, and we convert that to a volume of water using Gay-Lussac's law, so using the molar ratios. So we're looking for water, and that equals 5.05 liters propane times that equation factor, which in these cases 4 moles of water divided by 1 mole propane. And propane divides out, moles divide out, and that's the volume of water, liters, and we get an answer of 20.2 liters water. Okay, now the second way we can do this is to use the volume of CO2 produced in the previous question. So you're going to use VCO2 because they're still related by mole ratios. And so that's going to be the volume of oxygen produced was 15.2 liters times that mole ratio, which is 4 moles water divided by 3 moles CO2. CO2 divides out, I forgot to write it, but there it is. Moles divide out and left the volume of water, and lo and behold, the answer is 20.3 liters H2O gas. So virtually the same. Okay, so you can solve that type of problem one of two ways. As soon as you have an amount, you can use any amount to go anywhere in the equation. All right, last question. So part C. What is the volume of water vapor produced at STP? Okay, now I have changed things. If 4.05 liters propane reacts with excess oxygen at 98.0 kilopascals and 27 degrees Celsius, what volume of water is produced at STP? So I've given conditions of temperature and pressure, and you have to recognize the temperature and pressure change from reactants to products. So that complicates things. That means we have to use the ideal gas law. We have to use it twice. Okay, so the first thing we're going to have to do here is find the number of moles of propane. And we do that by rearranging PV equals nRT. Remember, that's the ideal gas law. PV equals nRT to solve for N. So N equals PV over RT, and that equals pressure of 98.0 kilopascals times a volume, which is given of 4.05 liters. R is the ideal gas constant, 8.314 kilopascal liter per mole Kelvin, times the temperature. Remember, we have to convert to Kelvin, 27 degrees Celsius plus 273, that equals 300 K. And so notice the unit analysis is nice, everything works out, we get rid of everything, 101 a mole, number of moles of propane, 0.1591 moles. So that's pretty good. Next step is simply to convert to number of moles of water vapor. Remember, we're looking for water vapor, so NH2O, using conversion factor, number of moles of propane, 0.1591 moles propane, times, I'll just go back to the equation so we can see it, 4 moles of water over 1 mole of propane. And so now, again, unit analysis, propane divides out, moles are gone, we're left with the moles of water, and that comes to 0.6365 moles water vapor. Now, last step, we have to use PV equals nRT again, but we are after the volume of water this time. Volume of water equals nRT over P equals 0.6365 moles. R does not change, still 8.314 kilopascal times liter divided by mole times Kelvin times the new temperature, which is standard temperature, which if you recall is 273 Kelvin, 0 degrees Celsius, divided by standard pressure, which is 101.3 kilopascals. And the units divide out nicely, as they should, and we're left with a new volume of water produced of 14.3 liters to the correct number of sig figs. So that hopefully quickly reviews gas stoichiometry using the law of combining volumes when temperature and pressure are constant for reactants and products, and using the ideal gas law. And that concludes this video.